Quantum entanglement theory 1. Single wave with dual expressions. In this theory, quantum entanglement is not the interaction of two separate particles, but rather the expression of a single wave. This wave exists in a superposition with the potential to manifest itself in multiple states or forms such as two particles. 2. Opposite excitations and spins. The wave is described as having dual expressions, where the wave manifests as two distinct particles. These particles are not separate entities, but are two states of the same wave, with one having an upspin and the other a downspin. These spins represent opposite excitations of the wave at the point of manifestation. 3. The crack of the whip. Sud. The transition from a superposition to observable particles occurs at the end of this wave's excitation. Think of this transition as the crack of a whip, a sudden release of energy or change in the system where the wave function collapses into definite states, the particles. The particles themselves are the localized, measurable manifestations of the wave, but they are simply points at the end of the wave's excitation. 4. Non-locality of the wave. The wave itself is non-local, meaning that its influence or existence is not bound to a specific location in space. The particles, when observed or measured, exhibit correlations, such as opposite spins, instantaneously, even if they are far apart. This behavior arises because they are expressions of the same wave, and the entire wave is inherently connected, regardless of spatial separation. Number 5. Particle expression. When a measurement is made on one of the particles, e.g. determining its spin, it forces the wave to collapse into a localized state. The second particle will instantaneously adopt the opposite spin, not because it is communicating with the first, but because both particles are merely different expressions of the same wave. Conclusion. Quantum entanglement in this model represents the dual manifestation of a single wave into two particles with opposite excitations, such as spin. The crack of the whip signifies the point at which the wave collapses into a measurable particle. The entangled particles are not separate entities, but are merely distinct, localized expressions of the same underlying wave connected in a non-local fashion.